greetings. In this one, we'll be talking about what is a group action a bit, and also about what is a stabilizer in that context. So, a group action is when we have some function, let's say f, where, and there's left group action and right group action depending on the order in which this operation is carried out. But we'll be considering left group action because that's usually the first one to look at. Basically, you'll see why I'm talking about it this way in a second here. So left group action, or let's say group action, is this Cartesian product where group G acts on some set capital X, and it results in some other element in X, or the same element in X, depends on the case. So basically, we have a pair, an element from the group G and an element X from X. So that small g is in that group G and that small x is in that set X on which the group G acts. So what this, if I'm going to pronounce it in the group action way, this says group G acts on X. Alright, and this is a left action. If we switch the order, when X cross G would be the way we wrote it, then it would be a right action because the G is on the right. But here we see the G on the left. We call it left action, or shorter, just group action. And so what we have is this pair G and X, G from group G and X from X, and that will go to some element X, lower element X. So let's say this is x1 and this would be x2, but I mean, these two x's can be same or can be different depending on what that g is, of course. Alright, so now let's see, there's two axioms for this. So first of all, the identity element of G should, and let's say this is a dot, which means when this one element from G acts on that one element from the set X. So basically what we're talking about here is we put the elements of some set X in under the operation of what elements of G do to it. And mostly what we'll be looking at here is the group is a group of permutations. So let's say we have some numbers, and those are discrete functions that tell us, okay, if you have an input of this number, the output will be this number. So that's how this group will act on that set, where that X, when that set X will contain some numbers. And that G, that group G, just tells us which number will be moved to which number. So that's the point here, okay? So the identity element of G, when acting on an element from the set X, lowercase x, should result again in X. And for X, first axiom of it. Second axiom is, if we have some, basically the idea is, when we have, this is a cross, alright, this is not lowercase x, but this is like a cross, like when we define Cartesian products. And when we want to write down, the most common notation is, when some element from the group G, lowercase g, acts on some element x, is we put this dot there. So that's why the first axiom was written down with that notation. The second axiom is basically, if we have, there is a sort of associativity for when we have more one or another element of the group G acting on an element of X, where you have basically something like this. When H acts on X, like this, is the same as if GH together, which will be, I mean, for this is for GH belonging both to the group G. The second axiom, we have an element of G that can act on any element from that group, can act on any element of the set X. So G and H are both in the group, and if G acts on some element X, then it results in something. If H acts, it results in something. But we have this sort of associativity here, that if we have H and then also G acts on it, it's like if GH, whatever element, because group is closed under its operation, right? So if two elements are put in operation together, it results in a third element in the group. If this thing altogether acts on X, That's what it's equal to. Alright, so that's the second axiom. We have this sort of associativity there. It's like if we have a permutation, like we have 1, 2, 3 goes to 3, 2, 1, and we have another permutation, 1, 2, 3 goes to 1, 3, 2. These two permutations, if we want to like multiply them as elements, well, it's function composition, how they're put together, and this will produce a third permutation. So if we're talking about this, acting on that element x in the set x, it's like if just this result of when we shortcut this into what actual permutation, when we combine these two, what that results in, well, it's equivalent, alright? So that's the same idea. I mean, we can just say, okay, these two, we can multiply the permutation into a single permutation that will have something here. And if that acts, it's equivalent as if these two act in a row, as they're written. And of course, if you multiply permutation, by the way, and this is, we're not going to be going that close to it right now, perhaps, but by the way, this is, by the way, note, permutations when multiply from the right to the left. So I mean, you first regard what the outputs of this one are, that you put it into this one. That's how you process it. Alright, so anyway, this is group action, and let's have some example of how that can work. Oh, symmetric groups are the number one case we are looking at. Symmetric groups, alright, and let's say we have S3, so groups of permutations on 3 letters, so-called. So we can have 1, 2, 3 going back to the same, so nothing changes. We actually have 6 cases, alright. I mean, we can write these using cycle notation as well, but I mean, we don't have to. But let's just write down which ones we mean here. Alright. I mean, we actually don't have to write all of them immediately, but it's actually not going to take that much time, so why not do it? And which ones are we missing? We're missing only 1, 2, 3, 1, 3, 2. Alright, so it's 6. It's always this n in the index prime. Factorial, not prime. Factorial. So 3 factorial is how many permutations there will be for 3 numbers. Like changing their order, you know, in the second row, that's where their order is changed. That's how you write down permutations. But that's necessarily good to know before going to like group actions and such. I definitely know this first. So we have this, and what it can be, I mean, an example. So if we had a group action, gx on the set x, well, we can also say, what is, okay, so we say the group is that S3, as an example, right? Is that S3, and that set x will be what? Well, we can just say 1, 2, 3, alright? I mean, it can be more complicated, but I can give now examples, alright? So if I say that I pick one of the elements of the group, where our group is S3, so our elements G1, G2, G3, G4, G5, G6 are these elements of the group, they're permutations, and so I ask just for it to act on some chosen element of the set on which we act, on the set X. So my G I choose will be, and let me now also write in cycle notation. So in cycle notation, this would be 1, 3, 3 goes back to 1 and 2 stays, so this would not be written, but I can just write it down. So let's say my G is the cycle 1, 3. This is just cycle notation, a different way to write down the permutation. But I'm not going to go into this because this is also very important to know perhaps before going to group actions. So I would recommend to know this notation and also permutation groups, of course, and also this notation first. So we have this element G, and let's say our element, chosen element for the set X is going to be, I don't know, 1. Then if my G acts on this element X, it will result in, what will it result in? Well, it means my permutation, which sends 1 to 3, X on 1, so the result is 3. It's namely 1, 3 acts on 1. That's 3. Okay, so this is group action. Basically, you just take the group, perhaps permutation, group of permutations, then you put the number, and of course the output of that permutation for the concrete number is that. And of course, it doesn't have to be just clear numbers. It can be also a power set. I mean, all possible subsets of this set, of this discrete set, can be an example, all right? So, I mean, that could be, we can still have S3 as our group, but the set X can be something a little bit different. Let's say we have a set of sets which are 1, 2, 2, 3, 1, 3. Or let's take these, all right. All 2 element subsets of 1, 2, 3, and now we can act on them. And what we can do, by the way, and this is the identity element here. So you see, this axiom is also satisfied, of course, for this example, because E of our group, the identity element, when acting on any X will be X. Why? Because 1, 2, 3 is a permutation sending it all to the same number. Whatever number it acts on, let's say 1, it will be 1, on 2 it will be 2, 3 will go to 3. Alright, so now we have this, and of course we also always have to realize and think through what it will result in. Where will we get with it? And that's what we're seeing here. So for example, in this case, again we'll be doing the same idea. Now the elements of the set is actual 2 elements subsets of 1, 2, 3. And our permutation again will be doing basically the same thing. It will just go through every number and send it to where that chosen element of S3 would send it as a permutation. So 1, 2, I mean if I choose this one, then 1 will be sent to 2, so this will become 2, and 2 will be sent to 1, this will become 1. I mean it will stay in this case. See, the order of the 2 numbers in the set will change, but the set doesn't have defined order, so it's the same set, right? Basically, in that concrete case I showed here. So if we have this, then there's this. And what we can also have is not necessarily S3, but we can have, for example, some subgroup of G. And let's say that subgroup could, for example, be, we need to choose, to make a subgroup from S3, we should choose an element. That will be the identity, first of all, which is the 1, 2, 3, 1, 2, 3. And the second element, perhaps, which will be the inverse to itself, which is, for example, this one. So 1, 2, 3, 2, 1, 3 is an inverse to itself. So we have an inverse for every element. For that only non-trivial element, it's not the identity element itself. Let's choose this one, because it raised to the second power or put into operation with it, self is gonna result in E. So it's a closed, the operation is closed for this group, so it's a functioning subgroup, and it's good. So now we chose this as an example of a subgroup, and now let's try to just take a subgroup, or this group, and let's try to see if we can just put it into, let it act on the set X again. Now our chosen set is set X on which we want to act, is this set of 3 subsets of 1, 2, 3, two element subsets. So I will say this could be called with another letter, and it's group H acting on the set X, and it goes into X again. So let's see where that leads. When we, for example, take some element from X, which let's say we take first the 1, 2, and let it be acted on by all elements from this H. Now, this is useful. We have a subgroup which has less elements, so we don't have to take care of all these. And we can see what happens if we let H act on with all its different elements on this one element from X. So let's see. So if E acts on this element, well, it's just like if E acts on each of these 2 numbers, it's gonna leave them the same. And if the other one acts on them, so 1, 2, 3, 2, 1, 3 acts on 1, 2, what it should do is it should leave it actually same also, because 1 and 2 are switched. Their order as written down will be perhaps switched, but it's still the same set. So if I want, I can just say what results did we get when, or what sets did we get when we let H act with all its elements on the element 1, 2. Well, all sets we got were just 1, 2. So when we let H act with all its elements on 1, 2, we just got this same set 1, 2. And let's try to do this for, let's say, 2, 3 now. So we fix the 2, 3, and we let H as a group action act on it with all its different elements as a group. So let's let H now act on 2, 3. So if we let H act on 2, 3, it's E acting on 2, 3, which will be the same. And if we act with 1, 2, 3, 2, 1, 3 on 2, 3, we let this permutation act on these two numbers individually. So 2 will go to 1, and 3 will go to 3 again. So when we let everything from H act on this chosen element 2, 3, we see that the results were 2, 3 and 1, 3. So we see that there is no intersection yet for like when we let all elements from H act on a particular element, we see the result is not like if we let it act on this element, the results are not going to intersect when we let it act on this element. So now let's see for 1, 3 what's going to happen. So already for 1, 3 we know, let's just write down the results. If we let everything from H act on 1, 3, of course we're going to get 1, 3. And the next thing we're going to get is 1 will go to 2, so we get 2, and 3 will go to 3. So 2, 3. So again we get the same now. So we got these two again. So either the result will be exactly the same elements or disjoint from it, some elements with no union if we were to compare the two results of H acting on everything, everything from H acting on one element of X compared to another. And what this is, it reminds one of congruence classes, when basically the set of elements of X is separated out into disjoint subsets. It separates X into disjoint subsets. And it's true. There is equivalence relations in this. And this is called, it has a name. And before we wrap up this video, I'm gonna say what that is, how it is called. We can get some more space, although on the right side not necessarily that much. It's called orbits. So when we are able to let everything from the acting group act on the set, we see that the results of that will separate the set into disjoint subsets. Sometimes there will be just one subsets of the whole set X. So anything we let, whenever we let a subgroup or subgroup act on that set, everything, the result of it will be it will cover all the elements of that set directly. Sometimes it will separate it out. In this case, we saw one element was one class, and then the second disjoint will cover the rest of the elements of the set. So we will have it separate like that. So an orbit is basically when we let G, it's actually denoted around like this, is basically when we let all elements of G act on a particular one element from the set X. Alright. So that's an orbit. So these will be equivalence classes, and we will go deeper into it in the next one. But we saw that example that showed it with a concrete case, and yeah, that's what happens. So first thing, if you want to just reiterate the main points about group actions for this intro, is it's a group acting on some set, and then the results land in that set. There's these two axioms: the identity of the group will not change that element from the set, and there's this also sort of associativity, which best illustrated, for example, with composing permutations, which are functions. So we can act one permutation and another, or we can compose them into a single new permutation and like that one new permutation act on that element from the set. So these two axioms. And then we also have something called orbits, which of course there's more properties to them, but the basic idea is they are the sets generated when we take one element from the set X and put it and let all elements from a group, a chosen group, act on it. And it's denoted as this group acts as a whole on that element from X.